Okay, so yes, welcome back. So let me start with few things we did last Thursday. So things we need. So consider the Ricci flow and what we. Okay. There's plenty of rooms, so it's can. So anyway, so what we did, we look at the backward Ricci flow. Okay. So then we consider this. We fix point x. We look at reduced volume. So this is the reduced length. So then this is Q and tau Q. And we proved that this is non-increasing with a backward time. Okay. So we did this by proving two things. So by actually in two ways. Maybe we just record some of that. First, we derived this is proved by using a basic differential inequalities. This is giving like this. And scalar curvature and plus okay. So all equivalent. This is true in the sense of distributions. Though we only prove this at a smooth point, but you with some actual efforts, which was done in chapter 7 in our book, so that to justify this in the sense of distribution. So then this becomes a differential inequality on whole manifold. Okay. So other way you did this, you can also look at pointwise version. Namely, look at look at these functions of z, okay, of tau, which is defined to be a tau of exponential of minus L x of L z and tau. Okay, then the Jacobian of L exponential. Sorry, no dz. So if I integrate this on the region where this is well defined, then we can then we can also get this fact here. So this one is also monotonically decreasing. Okay. So other thing I want to record here, which I didn't say last time, but it can be obtained easily by assembling this computation on the estimate on the Laplacian and and the formula on the d on the time derivative of reduced length. So let me just maybe record this. And before that, let me put this way. So this f z tau, okay, as the tau goes to 0, this is actually goes to you can think when tau goes to 0, you are just looking at a very, very small geodesics. So then this is actually goes to this essentially become local things flat. So this is become z square. Okay. So this norm is just the norm with respect to the inner product, induced inner product at the given point x. Okay. So z here is in the tangent space of. Okay. So this particularly implies implies this V, the reduced volume, of tau is less equal to, of course, less equal to V tilde x0. And then this is simply an integration of these things. So this is nothing else but just 4 pi of n over 2. Okay. And the equality holds. Equality holds if and only if this m, the g tau, is flat. So namely, in all this process, in this monotonicity, everything is become equality. So you will see low curvature contributions, and no, and so you see this is exactly just that. That means that will imply this is actually flat, no curvature contributions at all. Okay, the space is I just record the simple fact from which can be derived easily from what we did last time. The other thing I said is by sampling this estimate we had last time, which I record here, is we can also get an inequality of this type. Okay. So this is plus. Okay. So it's like a backward heat equation applied to a reduced length, and this is n over 2 minus Lx over tau. This is less equal to 0. Again, this is in the sense we did this. From what we did last time, it can be proved at the smooth points of Lx, but then it can be extended in the sense of distributions. So okay. So it's a bit different here. The operator is different operator. So only thing you want to do is to cancel that complicated integral k. Okay, the k, and so once you can do that, what left as differential inequality you want to have. So I gave a corollary here. If you look at this the minimum point. If you look at minimum point, this is always big equal to 0. So this is Lx, the minimum, is always less equal to n over 2 Lx minimum over tau. Okay. So at the minimum point, what I say minimum is a minimum of so there Lx minimum tau is a minimum of a q on n of Lx q of tau. Okay, tau. So from this inequality here, you can immediately see whenever this Lx minimum is surpasses n over 2, then the derivative becomes negative, non-positive. So that implies Lx minimum is always less equal to n over 2. Of course, you can easily check when the tau is 0. That's true. Okay, I mean when tau is 0, this is just the 0 functions. Okay, so this is true for all the tau. For all the tau. So namely, so this is there is always for every tau there is a q tau such that Lx q tau is less equal to n over 2. Okay. So at least there's a value. There is a value of air distance, which is small. Okay, small. So I need to use this fact today. Okay. So other things I want to say is I don't quite need it here today, but I need it this week. So since this is the things we used in deriving these inequalities here, we look at this h. Right? We define the h. This is minus 1 over tau of minus twice gradient r of x. X is a vector field, which actually x is a vector field. When we apply this x is a vector field along the area geodesics. So but in general, you can take any x. Okay, so this is depend only on x. Giving any vector field, you define this, and this is I said last time, and this actually appeared in the Harnack inequality proved by Richard Hamilton, except in the case when Hamilton studied, he used the time, forward time. So here actually we use the backward time. And so by using a maximum principle, namely you compute the evolution equation on these quantities, one can prove the following. Harnack is imply the following: if a curvature operator is non-negative, so then this hx is non-negative. Okay. So I guess I have to just be a bit careful here, probably. Let me say this is the other way around. I'm sorry. Okay. So it's a convention here. Now, in the original case, it's used a t. That's a positive. Just make sure. Okay. So it's slightly just a convention for I still have this, but this is for tau less equal to 0. Okay, let's put this way. Okay. So of course this is true when tau is sufficiently small because this term is very big. Okay. So maybe I put this way for tau. Yeah, as I said, in the original convention is Hamilton used t big equal to 0. So now we use backward time. Okay. So this can be, I said, this can be proved by derive. We already have an evolution equation for curvatures. So you apply those formulas to this case, you will get the evolution equation here. And using a curvature, non-negativity of a curvature, you can check, and you can check maximum principle can be used here. Okay, I'm not going to do that. That very good reference. For example, you can look at the band Bock. On Ricci flow by MS. Okay. There's yes.
If there's a finite time extinction, then does Hamilton's Harnack inequality do anything? Because then tau less than or equal to 0 is after the extinction time.
Tau is negative, right?
Yeah.
What's the
issue? It's tau defined as being t equals the extinction time minus the usual flow direction.
Yes. So tau is like negative of t. So this time.
Yeah. So if we have capital T being finite,
finite, yeah. So this is true up to finite time. So. Okay. So this is only true whenever flow is defined. Okay. But when we use it, apply this to a so-called ancient solutions, and tau is true for all the time. So another thing I want to recall is which is again is some basic tool from Ricci flow, which I think I will take this opportunity to make to tell you what that is. It's useful technical part. So that's called maybe I put this side. So it's called the high derivative estimate. So high order derivative. So this is originally due to Xi, and but in this slightly improved, refined form was actually told us by Penglu. But okay, so this is a following. So that's it's a typical things for geometric equations, namely. You need to bound the curvature in this case, then you can bound the rest of things you want. Okay, so let's fix the statement is the following. Okay, so fix the k positive, okay, and alpha positive, and L is integer bigger to 0. Okay. So then there is a constant depending on k and r. K is the integer. There is a constant ckl prime, which depends on a few things, k and alpha and r and so on. Okay, such that the following is true. So again, GT is a Ricci flow. GT and 0t. Okay, and maybe I put it this way. This is local, some open set t less equal to alpha k, and the p of p of 0 r is contained in the U. Okay. So also we suppose we have a following bound. Suppose the curvature is bounded by k on the U. Okay, and also the derivative, current derivative, bounded by k on U, and beta is less equal to L. Okay. So this is so I need this is bounded by under 0 and t, and this is xt, and but here I only need the initial conditions on the derivative. Okay, so this is needed because we are dealing with nonlinear equations, so we cannot get a priori high derivative estimate without assuming certain bound. So then what I get is the k of r small k of Rn of xt is bounded on by a ck L prime of t of k minus L 0 over 2. Okay, this is on for all x t contain the ball of half radius times 0 t. Okay, times 0 t. So this is the so-called high order derivative estimate. And the proof is, well, I'm not going to give a detailed proof, but it's again, it's basically proof is not that difficulty. Basically, you're using maximum principle again. So what you do is you can prove by induction. I just indicate what proof is. Okay, on K. So for example, if you suppose it's true for k equal to n. Okay, so then you want to prove it for k equal to m. Then you set up the functions. So you set up a function, say fm, which is defined to be the following. You take some constant c, which depends on all the bounds you got before the m plus 1. So this is a t of max of m minus L 0 over 2, and no 2 here. Guess I put a square already. So then this is a t of a max of m plus 1 minus L 0 and the gradient m plus. Okay. So you make these functions, and you also set up set eta be a cutoff function such that this eta is identical to 1 on the half of a ball. Okay, and support of eta, you can easily find this. It's contained in the. Right, we do that because we only load these things on this in this open set, and the Laplace of eta is bounded. Maybe I just put some constant of depends on k alpha and Rn. It doesn't matter. Okay, so one more I want to have is over eta is bounded by C2 prime of alpha n of over R square. Okay. So basically what you are doing here, you just pick up eta to be a standard cutoff functions, then pick up eta prime, eta tilde to be standard cutoff functions, then just take eta to be eta tilde square. So then you have these things here. Okay. So then by direct computation, you can estimate the following. By direct computation, though it's pretty long, but it's rather straightforward. Just need certain patience, okay, to do. So you can compute because we want to apply maximum principle. So we compute eta. So there are many terms, of course, with especially when the m grows with many terms. But then you use induction assumption. So you already have a bound on this, and playing around a bit, you can easily derive the following. So some constant, small c1. So 0, this all these are some constant you choose, and then the capital C1, which I am not going to. So eta m plus 2 eta. And great. Okay, you can derive in the coordinate of this type. So then the maximum principle give where? So you are done. Okay. So I skip all the details, and as I said, if you can, we actually, so I said this is due to Shi, but he didn't. He just assumed L equal to 0, but we need this for all for possibly positive L. So we actually include the proof in the book for convenience. So you can check the book with the proof, okay, for the proof, and it's pretty standard, okay. So now with this preparations, we can prove and can go ahead to do what we are our main theorem today. Here is the main result. Okay. So the result is following: a fixed and the t less than infinity. So then there is a kappa. It depends on these two things, such that if m gt is a Ricci flow, it's a Ricci flow on a 0t, and maybe it's part this way, it doesn't matter. So maybe it doesn't matter, okay. So with m compact, okay, and we normalize the curvature at x0 is less equal to 1. Okay, the norm of that. So we normalize the curvature so that initially curvature is the normal curvature is at most 1, and the volume of P0 and 1 is omega, okay, for all the p. So furthermore, we also assume this curvature of xt is Just a moment. Okay, so maybe I do it. So then, okay, so then for any t0 less than capital T, R positive with zero. So, and P T0 in the M such that R M X T is less equal to 1 over R squared for all xt contained in a ball of a radius P T0 and R cross of T0. So then the conclusion is for all of these, the conclusion is the volume of this ball at the P T0 and R is big equal to omega kappa of R2. So maybe before I so today's main part of today's lecture is to prove this theorem. So this is very important theorem, though it's looks a little bit technical, because it says this is so basically this says so mg t is kappa long collapse. So long collapse simply means with a proper curvature bound, the volume is bounded from below. So it cannot be like have a very, very thin cylinder, for example. Long collapsed for on the scales on the are less equal to this quantity, because we require R less equal to T0, so basically R less equal to capital T here. Okay? Or in other words, R less equal to capital T. Okay? So you can take this as a definition. When later on, if I say this is kappa long collapse on a certain scale, that means this. If I say for all the R, this is true, then I say it's kappa long collapsed. Okay, for all on all the scales. Okay. So maybe before I prove this, let me give some motivation for this, because so why we need things like this. So maybe I give before I prove this, let me give an example, which I'm sure this was discussed before. So for example, we look at the M supposed to be R2. So this is supposed to be a cigar solution. Okay, cigar solution. So I look at the GT, say just to be a dx squared plus dy squared and exponential for t plus r. So xy simply coordinates on R2. So all I can say is G0, of course, is so this is simply is a phi t of star of G0. Okay, G0. So the phi t here maps xy to So you can easily check this is so one can check this satisfies the equation. Okay. So in fact, this is the same as to checking this G0 satisfies the ratio of G0 can be written as a Lie derivative of some vector field acting on G0. And this vector field is simply this. Okay. So this is called a steady soliton here. So this actually is true for t between minus infinity and plus infinity. This flow. Okay. It's a steady soliton. So as x, you can look at roughly it's one x, y. So let me rewrite this. So I look at G0. So let's say this is for simplicity, I write as a G. So you can write this in terms of the distance functions in the polar coordinates. So this is so rho is basic distance function. So rho is a distance to origin. Okay. So you can check this is basically near the infinity. This is like almost as close to cylinder because this is converged to 1. Okay. So asymptotic is like a cylinder. So you can actually make it more by direct computation. You can check the volume because close to cylinder. So this is so asymptotic to a cylinder. Okay. So that implies this is the volume of this. Of a ball, of suppose you pick up some point P here, say this P from origin O here, say is a distance is say 2 maybe 2r. Okay. So then you look at the P of this with this r ball, maybe 0 of r. Maybe it's actually for any t is like that. Okay. Okay. So using this, you can check this is for t for r. So this is roughly of like how do I say? So a distance maybe not r, a rho. Maybe I put a rho here. Okay. Rho below distance, r is the original. So this is basically some constant at the point of rho. Okay, because it's like a unit asymptotic, like unit cylinder. This volume for of course depends on t. For rho, say bigger equal to some constant depend on t. Here. Okay. But you fix t if a rho is big enough, you will have that. So it probably doesn't matter. It's anyway. So the curvature and the curvature is maybe let's put in a 0 case for simplicity. Okay, because everything is up to a diffeomorphism. So otherwise I have to adjust the constant here. Okay. So this is a curvature can be is basically 4 times 1 plus x squared y squared. Okay, so this is at order of total. Okay. So then you immediately find that you look at the point here and look at the ball of like this size. the curvature is sufficiently small, and this is, but the volume is not big enough. Okay, it's not at order of R. So that implies this is not. So this CK solution is collapsed. It's collapsed. Okay. So it's collapsed, and so does any the CK solution, say MR2 of this G cross with S1 and standard. So now this becomes three-dimensional. Okay. So that's because this is a fixed amount. It's a flat, so it will not change along the flow. So the volume will stay still the same, and the curvature stays still the same here. Okay. So it's a Kappa collapse. So this is so from the theorem here, it tells us we can rule this out. So that implies for any finite time for the flow, for any Ricci flow, okay. So for any Ricci flow in the theorem, so namely it starts from a compact manifold. Say there is no, okay. So there's no part. Say depends on some k, bigger k part contained in the M GT. Say such that k is diffeomorphic to a large part is diffeomorphic to say K0 in maybe a Kc inside of this say this guy, say it's M prime of GT or MC GC, okay, sigma in MC GC, such that, so let's see diffeomorphism through a diffeomorphism per psi, such that, so if I take say per psi is from let's write this way, Kc goes to a K, such that such that the Kc is sufficiently large. So why it is sufficiently large? Because this is sufficiently large so that this will contain part of this collapsed part, large, and the per psi of a metric is sufficiently close to maybe I put it this way. So it's sufficiently close to. So I scale it because after the metric it might have the curvature big. So I put Q. Okay. So maybe I put it this way. So we pull back this. So I put this way. So I pull back this per psi star. So then I evaluate at the 0. And then the Q inverse of T, I need to scale it. Scale the flow is sufficiently close to a GC. So where the Q is some point of norm of curvature at some point P. Say at some point T. So maybe I should put this way, because it starts from 0, so it's so this is plus T0. So it's Q, so P is contained in the K. So this is maybe I put, so P is contained in the K, and this is on a, I need this to be on a, maybe a 0 to a certain part. So this is contained KC, and cross maybe -1 to a 0. Okay. Maybe I put this way. Good. So Q is Q. Presumably, we look at this. Is Q is supposed to be very, very big. It's a part where the space becomes very, very curved because develop singularities. So we look at the part where the flow develops singularities. When we scale it to a unit size, then what we want to see, this cannot be close to a Cigar solutions, or close Cigar solution cross with some trivial factors. Okay, so that's and that's very important fact, as I said at the beginning, because that's if this is thing actually people try to, and Hamilton try to rule out too. So if this cannot be excluded, then you might need to do a surgery along the tori, right? Because across the circle, the boundary of this is a circle across this other factor circle. Okay, so once we can rule out this, then we can make sure at any finite time you does not need to do a surgery along the tori. Okay. So why it can be excluded? Because if this is true sufficiently close, then you will be able to find the part where this flow is collapsed. But this is contradicts to this theorem here. Okay, is that clear? Or any questions? Maybe. Okay, a little bit less precise, but it's these things I feel it's probably. It will be too tedious to write down every step. But anyway, so this is best. So this is outline the proof. This Cigar solution is excluded. Okay. Oh, any questions? You can. Okay. So now we go to prove this. Okay, so now let's try to, once we have this, we want to prove this theorem here. Okay. So we want to prove this theorem. So somehow this is a little bit too bad in that. So proof of a theorem. Okay. So there are few steps. So okay. So we want to use a reduced volume. So first thing, we make some claim here. So okay. So first, I want to say a claim. We assume RT0 bigger equal to 1. Okay. So why? So that's because the things we are doing here is a scaling invariant. So we can so if say a T0 is less than 1, so we can define a new metric, say G bar of dot T, which defined to be a Q of G. So maybe this is just 1 over T0, okay, of G of T0 T. So now this time the flow for this is defined on a t less equal to 1. So then the t0, t is less equal to t0. Okay. And you can check, because the scaling things dg bar dt is still satisfies the Ricci curvature equations. Okay. And so now this time is corresponding t0 for g bar is bigger to 1, is equal to 1 long. So, and the curvature of g bar, if you compute the norm, and this will be a 1 over t0, so it will be t0 times the corresponding curvature of g. Of course, you have to change the time. So this will still less equal to 1. Less equal to 1. Okay. So the volume of a ball with respect to g bar, okay, at the initial moment. So I just want to check assumption. All assumptions are true of a p of t0. So this time is 1 of r. Okay. G bar. So this is by scaling. This is just volume of g of b of p of t0 okay, so it's t0 r. Okay, t0 r. So I think I taking r equal to 1 here to check the conditions. So let's check 1 here. The radius 1 and radius 1. Okay, and the volume, but t0 less equal to 1, and I know at initially, I'm sorry, at 0, I'm sorry. So this is not changed. Okay, so this is also checked at 0. Okay, this is actually checked everywhere. It doesn't matter. It doesn't matter. Okay, so automatically this is true at 0. This is true. So if you look this, because at t equal to 0, I assume the curvature, then the volume comparison tells you this will be a big equal to some fixed constant, depending only on a dimension, okay, of a volume. I'm sorry, this is a ratio here, so I have to take a t0 to n. Okay, this is a ratio. There's a factor. Okay. So then this is big equal to a volume of g of b p0 1, because of volume comparison. Our curvature is Newton bounded. So this is still bounded from below by some, since omega is some uniform constant. So I still have this assumption here. Okay. And similarly, you can also check this assumption is true after scaling, because you decrease the curvature. So then if you can prove this for r, so then if you proved this, so that imply so if the kappa, okay, so if so then if kappa, if the theorem is true for holds for just a slow g bar, then you can say then the volume of this b of p of at t0 become 1. So then I can take r to r is less anything less equal to 1. So I can take this as a square root of t0. I'm sorry, this should be square root of that. That's the right scaling. Okay, I'm sorry. Okay, metric scale this will then radius is square root of that. So I can look at this times r. I'm sorry. So r, that's square root of this. Okay. So this will be less equal to 1. And this with respect to g bar. And this is bigger equal to 1. If a theorem is true, then the kappa may depend on this constant now over times r square root of T0. Yeah. So, however, this is same as the volume of G of BP of T0 of R, and then this is and then there's a scaling factor T0 to n over 2. Okay. So then you get both. Okay. So then you get theorem for G. For G, I guess it's a bit too. So anyway, so we can make this assumption here. So next observation is again a very so in fact every step is very easy. So next we have a following observation. So next I also claim so observation. Maybe I just claim 2. Okay. So there is a uniform. So there is a uniform constant A. Say depends only on dimension, such that the curvature of xt is less equal to for all and the volume of bxt of R maybe 1, okay, is bigger equal to some fixed constant, say maybe omega of a half of 1, okay, for all x in the M T A, maybe less than 2A for convenience. Okay. So basically we only need to bound the curvature. Once we bound the curvature, because the curvature evolve along the Ricci flow, so if so the change of a metric is bounded by curvature, so metrics are comparable to each other. So only thing, so basically this claim, the essence is these things here. Once we can bound this is automatically true. So why? Because you look at the evolution equations, right? So the proof is very simple. Okay. So you know the curvature initially is less equal to 1. Okay. So what you do, you can by an evolution of curvature, okay. So then we know we can write the evolution of a corresponding norm. So this will be less equal to plus some constant times O m squared. So then you can apply maximum principle. So suppose this is true for so suppose say Rn is less equal to in 0 of say A twice A, okay? And just to pick up A, okay? So maybe I put it this way, so T0, okay? And also the max of Rn at T0 is 2. Okay. So then you can apply this, say it's a so then this side, see some constant depends only on dimension here, because it depends on how many terms come out from the computation of curvature. So this whole thing is just, let's say, less equal to 4c. 4c here. Okay. So then what you can do is you know this is you consider solve let H be a solution of dH dt plus C plus 4C, and H at 0 is 1. So that will imply this by maximum principle, that imply H is bigger or equal to Rn. T0 using these two things. So then we are done. We know H is just some standard heat equations. Unless the T0 is sufficiently has certain, it cannot be too small, right? So T0 cannot be too small because so this is a big, so that implies H is bigger too. So that implies T0 is bigger or equal to some constant. Okay. So this proved this claim to here. So now next thing we do is the following. So we look at we draw the picture. Suppose I have so we look at the tau to be a T0 minus T, set this, okay? And the tau equal to 0 corresponding to a T0. T equal to 0. So when the tau is a big equal to a, say a big equal to a T0 minus AN, AA here, that means or minus 2A, that means this is that means tau T is less equal to A. Maybe put this way. So now I look at the things. Suppose this is our manifold. So this is at T0. This is at T equal to 0. Okay. So we pick out some point. And so we pick out some point here, which I set to that P, which we will compute. We will bound area from below. Okay. So then we look at say T equal to A. Okay. So then we find that there is a point at t equal to a, so there's point q of a here. Maybe should structure t0 because in terms of a. So that's guaranteed by, I guess, I erased. There's a minimum point. So this is corresponding to a okay. So there's L geodesic here, gamma. Okay, so L geodesic. So where so L P of Q of T0 minus A, T0 minus A is less equal to n over 2. Okay. So now you fixed this, say, let me set this point of Q0. Okay. So this is Q0 for simplicity. So then we look at the small ball of a radius 1 here. So for any Q contained in the ball of Q0 of say 0 of this 1. Okay. So then the things for this for t less between 0 and a, we have this bound. So then we look at just the geodesic drawing a Q0 to a Q by a G0 geodesic. Say it's a gamma Q. Gamma Q. Okay. So namely the length of this G0 of a gamma Q is less equal to 1. So that will implies this integral. You look at L, okay, of L length of a gamma Q. So this is from an interval from a T0 minus A and T0. Okay. So this square root of tau and the scalar curvature and plus gamma Q prime square. But this is measured in terms of tau. So for this region, so our curve is here basically. So starting from this, I get some Q. So maybe I'm sorry. So some Q0 here, and look at the unit ball here. Look at any Q. So then I join them by geodesic here. So this is gamma Q. Gamma Q. So gamma Q is since for this region, all the curvatures are bounded. That will imply all the metrics are comparable to each other. Since we'll do a similar thing later, let me see. So this is all bounded by some so it's comparable to G0. Maybe up to a factor of plus or minus of n minus 1, 2 of A. Okay? That's well, I use the Ricci flow here, so I guess I need a 4 here. Okay. Because curvature, each curvature is peak curvature is less equal to 2, so Ricci curvature less equal to 2 times n minus 1. So, but the change of a metric is given by twice of Ricci curvature, so it's like 4 times n minus 1. So that's why you have this. Okay, so you bound this. So everything here is you can replace this by G0 and just up to a factor. So anyway, so this is this is bounded from below. In fact, I probably don't need that much. So I can simply drop this. I'm sorry. So I try to give more precise things. So I only care about this. So this is less bigger equal to, because I only bounded from below. So this is just a moment. I got something. Just a moment. So okay. Yeah, I guess okay. That's fine. So, all right. So I guess what I do is I still need this. So anyway, so this is bounded by this is big equal to a T0 of A of T0. Okay. So anyway, it's bounded by some constant. Okay. By some constant. So this constant depends on these two and depends on dimension n. Because that tells you how many components needed here. Components. So once I have that, so I can I can join this curve. So that implies LP of T0 is less equal to, first I go from is less equal to LP of gamma from 0 to T0 minus A, and plus LP of then plus length of this gamma Q. So this will be less equal to n over 2 plus Cn. You can make precise bound. It's probably less equal to A times n. That's probably, I guess this is probably just A times n is big, good enough. Okay. So what is a good thing here is then we get upper bound. So that implies this. If I look at this V tilde of at T0 of P, this is big equal to 0 of n of T0 of n over 2 of exponential of some constant, some constant C, say some C prime n over twice of what is definition normalization factor. Okay, so then this is T0 here. So dq. Okay, so this is bigger to on the ball of Q0 of 0, 1. So then we are done. So this is big equal to some constant. Okay, so chi pi, say So let's say kappa 0 here may depend on t, because t0 depends on t, and the dimension n, and omega, because you need to have a no-bound volume of this. So by monotonicity, so I know the Vp tilde of tau prime, tau 1, will be less big or equal to chi. Okay. So now I want to derive a contradiction. So tau 1 is a small. So tau 1 will be small. Will be near here. Okay. So here I have a ball of a parabolic ball where curvature is bounded. Curvature is bounded. I have a parabolic ball defined here. Defined here. Okay. Defined here. So okay. Okay, so now how do I do it? So I take tau 1 to be set tau 1 to be this quantity. So let me okay. So now I set epsilon to be this volume of a BP T0, okay, and T0 and R divided by R. Okay. So I want to prove this the epsilon is sufficiently big, bigger than some constant kappa here. So kappa is related to that kappa 0. So let's say so. Okay, so the volume of this now. So I want to prove epsilon is sufficiently big. T0 R is epsilon to n, and R to n. Epsilon R to n. Okay. So basically, since the ideal here is I want to prove this guy of P of epsilon. I choose this to be epsilon R square. So this is my tau 1. Okay. If epsilon is small enough, of course epsilon R square will be much smaller than this. Okay. So I want to say this is I mean R is less equal to T0, so this is bound. So I want to say this will be small if epsilon is sufficiently small. So then I will get contradiction because this is contradict to this. Contradict to this. So now I want to bound this from above when the epsilon is small. Okay, when epsilon is small. So from now on, I will assume epsilon is small. Maybe I erase here. Don't need this anymore. So now let's bound this. Okay, so how do I do that? So recall we have this V U of P of tau 1. Okay, so this is a u tilde, a u. This is all the point in the x in the manifold, such that there's a unique air geodesic joining a p to x. Okay, and within this time, okay, in a 0 tau 1. Okay. And we know this is open dense set. So this is a dense, open and dense in M. Okay, so we can basically we estimate integrals. We only need to estimate things here, and also recall the u tilde p is a pre-image of this. Okay. So now this is contained in the tangent space. So now I divide this into two parts. One part I call the W small. Why I call it W? Because in the book we actually prove more general. This theorem in a more general form. We don't look at the whole thing. We look at certain region. So I adapt the notation there and call W notch. Okay. So where the W small is defined to be all the z inside the TPM, such that the norm of z is less equal to 1 over 8 EP. So it's a region where this maybe square root of that. Sorry. So it's a region with certain bounded. So W notch. Of course, I should say this is contained here. Let's put it this way. That's the only thing I need. Okay. So this is large, means z, and the norm of this. Okay. So then my integral become two parts. The v tilde of p become integral of w small, okay, of this tau 1 of n over 2 exponential Lxp of tau 1, and then the Jacobian, and plus w large of same thing here, okay, of same thing here, same integral here. So the large part is easy to do. I guess my time is goes fast. So I have to go a little bit quick. So let's first check for second integral. So this is 1. I guess I was a bit too slow there. Brilliant. So for 2, we apply the following because so for each z, okay, so we can apply a monotonicity. So this is decreasing. We look at this f. Remember this fz of a tau, which is defined this function. We define this tau minus n2 exponential minus p of tau, and the Jacobian of air exponential map. Okay, this is Jacobian of air exponential map. This is monotonic decreasing. So this is particularly less equal to f of z of 0, right? So that implies f z of tau 1 is less equal to that. So this is equal to I said at the beginning, I forgot now. So there are some constant. It probably doesn't important. Anyway, important is that factor. Okay, I may be wrong about this constant now. So then this part, so that implies bimodultricity. So this large part is simply less equal to integral of z of bigger equal to 1 over 8 square root of epsilon of twice of n of exponential of minus z square dz. Of course, this will be very small. So this will be, say, less equal to, as long as epsilon small enough, so this will be less equal to epsilon n over 2, say. Okay, if epsilon small. Okay. So I have no problem with this. So only thing I need to check is this part. So I need to take a few more minutes now. Okay, and a bit rush. Suppose this. I think. Oh, okay. Maybe keep that picture. So then what I want to do is I want to do a following. I want to claim this. When the z is sufficiently small, okay. So for 1, I want to estimate 1. For any z, for any say q contain is equal to L exponential of p of z here. So z is in the small, w small. Okay. So I want to say so let gamma z be the geodesic, unique geodesic, L geodesic from 0 from P to Q, okay, equal to gamma z of tau 1. Okay. T equal to T0, and I have a P here. So I have a parabolic ball. So I want to say this is so I said this is a parabolic ball. Then I shrink the size by half. Okay. So this smaller one says so this is maybe a smaller one, and the smaller one is a b of p of t0 of r over 2. So then I only look at the time from t0 to t0 minus tau 1. So I only travel a little bit. So I want to say this will stay here. So maybe I claim claim of this and assume this. Okay. So I claim the following. Then I come back to, I want to say gamma xz of tau is always contained in the bp of t0 of r over 2 for any tau less equal to tau 1. Okay. Of course, z is in a small region. Okay. So once we proved the so this is actually prove the following. So then what I guess this is okay. So I claim this, and this is actually proved in the following way. So okay, So I can first let me claim this. Okay. So then I want to get a corollary of this. So this claims 3. Okay. So corollary is the following. As long as y inside here, okay. So claim for all on the B of x t0 r over 2 cross this interval t0 minus tau 1 t0. So I have a gradient. We have a gradient of scalar curvature that's equal to C1, some uniform constant cube, and 1 minus C epsilon of G. So first, this is this estimate. All these estimates are scaling invariant. You can make r to be 1, for example. So then the time you traveled, if r is normalized to be 1, the time you traveled is exactly given by epsilon. Okay, because tau 1. Remember, tau 1 is epsilon r squared. If you normalize r to be 1, then this is. Okay. So sorry, the t is inside here. Okay, t is inside here. So since t only travels to epsilon, then you have this. Why? Because you know the curvature bounded. As long as you are staying in this region, by assumption, the curvature are bounded. Okay? As long as you stay in this region, the curvature are bounded. So then you have this bound. And you have this bound because of high order derivative estimates. Okay? So this comes from high order derivative. That's why at the beginning I need to say that, okay, to take the record. Of course, that estimate is not only used here; it will be also used in some other places. So once I have this, then what you can get is the following. So once you have this, so suppose I have this. So then and so it's not a corollary. So this is observe. Okay, sorry, I'm a little bit. Okay, so then the corollary is the following. Okay, then the corollary is if x, as before, is this gamma z prime. Okay, so then we know this is by assumption of tau goes to 0. Square root of tau of x is z. That's by definition of z. And we have a following things. The square root of tau of x minus at tau and measured at gt0. Okay, the norm of that, and minus the z is bounded by twice of z. Okay. So this is because it's easy to see because you have a geodesic equation. So geodesic dx x minus half tau of x minus so, or you can equivalently, it's easy to see. So if you remember as is twice of square root of x tau, then this dA is equal to minus tau s squared. So A here is simply where the S is square root of tau. You can reparameterize. Okay. So then this is basically geodesic equation except these corrections from Ricci curvature, Ricci flow. And since curvature are bounded, and derivative of scalar curvature are bounded, then you know how the change, how the norm of change, how the change in the vector field. You can control the change rate of change of vector fields. So then you can get this just by fundamental theorems. Okay. So on the other hand, and this you can also back to here, because as long as this curve stays here, you have a norm control. You have, namely, you can bound the derivative of this. So then you go back, use fundamental theorem again to prove it can never go beyond this radius. Okay. So once this is all proved, so that's so in the end using this. So if I assume this side here, I can have this. So in the end, what claim is I want to say this is this for. So I get this is and how do I say? So maybe I finish this. So just a moment, I guess. In 1 minute we are done. So once we have this, so I just maybe to check what. So then the Lx has a control, and okay. So now once I have that claim now, so then we look at the Lx of and Lxq of Q is this thing here in the tau 1. Okay, so this will be by definition this 0 to tau 1 square root of tau of R plus. Okay, so this will be a bigger equal to, and this is non-negative, so I can drop out. So this will be less equal to a bigger equal to tau 1 of square root of tau. Then the low bound of curvature is because assumption. Okay, d tau. So here I used this bound. Because the L geodesic will stay in this region. Actually, we are staying in a smaller ball. So then I can use the assumption on the curvature. Okay. So I integrate this out. So I get this is 2 over 3 of n minus 1 and epsilon. Tau 1 of 3 over 2 of R square. So this bring the tau 1 in. So this will become a 3 over 2 over 3 of epsilon. of 3 over 2 of R. So R, okay. So then we are done. So air length, so that implies air small. So this is air X, air P. Sorry, this is P here. So air P of Q of tau 1 is big or equal to air P of tau 1 of square root of tau 1. And this will be 1/3. Okay, and I have an epsilon square root here, so I get epsilon. And this is gone, and R is gone. Okay. So I bound this, so then we are done. So why? Because then the V P tilde, this integral of W small. Okay, so this is tau 1. Okay, and D. Okay, so this is same as so this is integral over Z of J dZ. So this is same as the air exponential map of a P of W small, and then this is tau 1 exponential air P of Q tau 1 dQ. So this will be less equal to, because of this here, exponential of 1/3 of n minus 1 epsilon. Then the integrate this. So this is so this will be so certainly will be bigger equal to sorry, let me just do this. So this will be bigger equal to less equal to this on the ball of P of T0, because all this in R over 2, right? Because all this we just prove it's nice in these things. So this is so I take a Q and times tau 1. And this whole thing, some constant, maybe just put Cn here. Okay, and this is epsilon R squared minus n over 2. And then you have the volume of this, so which we already said this epsilon n over Rn. Okay, by definition. So this is this will be less equal to volume of B P T0 R. So this is epsilon n Rn. So this will be Cn. Actually, this you take epsilon sufficiently small, this is less equal to 2. Okay, so then the epsilon n over 2. So you put them together, combine them with 2, you will get something like bounded by some constant. So in fact, that take epsilon to be small, so this is maybe less equal to 3 times epsilon n over 2. Okay. So that implies, maybe I put it here to finish. So if epsilon small, then the reduced volume of P at tau 1, so that is epsilon R squared, is less equal to 3 times epsilon. But on the other hand, we know this is bounded from below by some kappa 0, by multiplicity, so that's a contradiction. So epsilon cannot be too small. Okay, so kappa exists. Sorry for overtime. So I give you back time later. Okay.